All right, so in this example, we're going to look at how the limiting reagent problem works out with the butanol, which is this substance right there. And then you have some oxygen that it burns with to produce carbon dioxide and water. So this problem is going to be kind of a classic example because it gives you amounts of each substance, 4.227 grams of butanol and 8.093 grams of oxygen gas. So basically, once you know you have two substances or two reactants and you're given amounts of each of them, it's going to be a limiting reagent problem. So let me go ahead and talk strategy real quick, right? So the first question is asking about limiting reagent. I'm basically going to take the amount of butanol that I have here, so that's my butanol, and I'm going to basically solve for the amount of CO2 that it can produce. And then I'm going to do the same thing with the other reactant, in this case O2, the 8.093 grams, and I'm also going to solve for the amount of CO2 that it could potentially produce. I'm going to show that work up here. 4.227 grams of butanol. That's going to be C4H9O11. And then again, using my mole ratios and molar mass and whatnot, I'm going to figure out how much CO2 can be produced. I'm going to actually stop at the mole amount of CO2. You can keep going if you want, but just for the sake of having just a number to compare, we'll stop at moles. So the molar mass of butanol is 74.12. And then that's going to be equivalent to 1 mole of that substance. And then I'm trying to compare it to carbon dioxide. I'm trying to figure out how much carbon dioxide will be produced. And so the ratio is for every 1 mole of C4H9OH, it'll produce 4 moles of CO2. That's going to generate a number, but for the sake of keeping things moving, I'm going to go ahead and do the other part. So the other part of this for solving for part A is I'm going to take the 8.093 grams of oxygen and basically perform the same task. So I know that this O2, if I assume that all of it's going to get used up, I can potentially produce a certain amount of, 6 moles. I can produce a certain amount of CO2 that I can then compare. Okay, so then I do a little bit of math and I get 0.2281 moles of CO2 that could be produced. I'm going to do CBP, could be produced with the 4.22 grams of this butanol. Assuming all that butanol is reacted, I can maybe make, but I can make, again, on paper, this many moles of CO2. Then for this other one, 0.1686 moles of CO2, again, could be produced if I reacted all of my O2, assuming that my other substance was in plenty of excess. So comparing these two, my oxygen ends up being my limiting reagent. So my limiting reagent is the 8.093 grams of O2. Right? Again, because it can produce less, right? It can potentially produce less. It'll run out before the other amount of C4H9O, the butanol, will be used. The second question is B, what is the maximum mass of carbon dioxide that can be produced? All right, so looking over here, I'm going to kind of look at these two numbers and decide on which one I want to do. Well, since I know this is my limiting reagent, pretty much everything else in the problem should be based off of my limiting reagent here. So this mole amount of CO2 that could be produced is actually not even could be produced anymore, is going to be produced. Right? Since that's going to be our limiting reagent, we know all of that oxygen will be used up, so therefore we know all of it will be produced. So to finish this one out, I'm just going to do a quick molar mass to get from moles of CO2, wrong way, from moles of CO2 into grams of CO2. Mole of CO2, 44.01 grams of CO2, and that'll give you 7.420 grams of CO2. Right, that's part B. Done. All right, now this problem continues on the next page, so we'll remember some of those numbers and go back to it if we need to, but we're looking at this bit, see how much excess reagent remains at the conclusion of the reaction. So how much excess reagent? So going back here, we know that my limiting reagent that we just solved for in the previous step was the 6O2, or is the oxygen, the 8.093 grams of oxygen, right? That's our limiting reagent. And then our other substance, our excess reagent, is this butanol. So the question is how much excess reagent remains? So how much excess butanol remains? Now, how to do that? Well, in this case, like I did in the previous one, I kind of, just basically use simple stoichiometry to figure out information about CO2, right, as a comparison. But in this case, I'm actually going to kind of go backwards and say, okay, right, I'm going to take a look at my limiting reagent, and then I'm going to see how much corresponding C4H9OH was also used up. So in that case, I'm going to go ahead and take my 8.093 grams of oxygen gas, which is my limiting reagent, and then I'm going to figure out information with C4H9. It is asking for how much excess reagent. How much, again, generally is a gram amount. Usually it's kind of assumed. So let's figure out how many grams of butanol is also used up. So 32.00 grams of O2 for every 1 mole of O2. For every 6 moles of O2, you will also use up 4 mole, no, just kidding, 1 mole, let's get rid of that, 1 mole of butanol. And then, since I'll have a mole amount of butanol at the end of this, I'm going to go ahead and switch it back into grams. So 1 mole of C4H9OH, and then you get 74.12 grams of this butanol. All right, do a little bit of math here. And you get 3.124 grams of this butanol. I'm just going to do but as a shorthand right over here in the corner. And that's going to be how much was used, right? So how much of that butanol that was originally given is used. This is it, right? Because we started with our limiting reagent. We saw for other reactant, that's getting a corresponding amount of butanol will also be used with the oxygen. But again, that doesn't answer the question. The question is asking how much excess reagent remains. So broadly speaking, anytime we do excess reagent, it's always going to be your initial given amount minus the used amount is going to always equal to its remaining, right? The excess remaining amount. So we're just going to plug in the numbers appropriately. I know that the 4.227 grams minus the used part up here, which is 3.124 grams, is equal to the final answer of 1.103 grams of butanol remains. Okay, that takes care of the part C on this one. Part D, what mass of water will be produced in this reaction? So far we've basically ignored water this whole time. That's not to say it's not important or it's not there. It's just that, we've been focusing on the other substances. So the question again is how much water will be produced? Well, what should I base that off of? Remember, my limiting reagent is still the anchor to the rest of this problem. So if I know that that substance will all be used up, that means I can figure out how much H2O will also be used up. And by used up, I mean how much will also be produced. So let's figure this out. I'm going to do part D down here. I'm going to start off with the 8.093 grams of O2. I'm going to then get information about my H2O. So I'm going to go ahead and do 32.00 grams of O2. For every 1 mole of O2, apply the mole ratio that relates those two substances, 6 moles of O2. For every 5 moles of H2O, so 6 moles of O2 used will generate 5 moles of H2O. And then, because they're asking for the mass, we go ahead and change it out of a mole amount and apply the molar mass of 18.02 grams of agua. That gives you 3.798 grams of H2O. So that's how much water we produced as a result of this reaction. Now, notice again in this problem right here, it doesn't really ask for the maximum amount, but that's really again also the maximum amount, right? I can't make any more than this because my oxygen runs out. I don't have 8.094 grams, which would maybe produce more of this. So this is the maximum that I can make. Finally, part E, show that mass is conserved. So remember, conserving mass can be generally saying, what is used up, what your reactants are, is equal to what the masses are in terms of the total. But remember, you got to be careful because sometimes there's stuff that's not used up. So let's see how this works. First of all, let's go ahead and take a look at our initial amounts, the 4.227 grams of butanol plus 8.093 grams of O2. That's our total reactants. That gives you 12.320 grams of my reactants, right? That's how much was initially put in. Then on the product side, well, what do we have? Well, we figured out from the previous page, I'm going to scooch up here for just a second, right? We got 7.420 grams of CO2. 7.420 grams of CO2. We also just now in the previous step, part D, figured out that there is 3.798 grams of water, right? That are the products. So let's go and add those together, and you get 11.218 grams of products. All right, so there you go. Look at that, conservation of mass. But wait, what? That's not the same. Don't forget, right, this is a limiting reagent problem because we know that all of this is used up. only some of the butanol is used up. So really to keep track of it, right, this is not really the appropriate addition. What's left over in the end is also remaining 1.103 grams of excess butanol. Right, so if you add that together, let's make that butanol so it's easier to read, and then you add that together. So then you have the 12.321 grams, which again, that's a little bit of rounding there. But yes, now we can basically show that we have our conservation of mass. Okay, so that's basically, again, just keeping track and accounting of everything. So that's basically the rundown of this problem. Let's do the next one together. This one is going to take a little bit of extra work, partly because they don't give you the equation, but just to make sure we're on the same page, and we get this equation. So with this right here, right, it's balanced for you, 2, 3, 1, 3, 3. That helps us know that we can make some comparisons. Now, this problem right here, again, does say that you do have a sample containing 18.1 grams of ammonia. It's reacted with 90.4 grams of copper oxide. Which one's your limiting reagent? How many grams of N2 can be isolated? All right, so once again, if you recognize it, right, we're given amounts of each reactant, 18.1 grams, 90.4 grams, and then we're being asked to solve for limiting reagent. So therefore, it's a limiting reagent problem, or limiting reactant problem. Let's see how this is working out. So which one's our limiting reagent? I got to do a little work. 18.1 grams of ammonia. 17.03 grams of ammonia as a molar mass per 1 mole of ammonia. And then we know that the ratio is 2 to that, right? Why am I choosing N2? Not just because it's first, but because the question's asking you about how many grams of N2 can be isolated in a later problem. So I can go and plan ahead and say, oh yeah, I can go ahead and do the comparison between 2 moles of NH3 for every 1 mole of N2. Now, at this point, it's kind of a judgment call. I know we're going to get to grams of N2 eventually. That's our goal. I can go ahead and plug in molar mass here if I want, but I could also stop here and just get a mole amount of N2 and still get the same result. For the sake of, again, planning ahead and knowing I'm going to look at the next part, let's go ahead and stick in the molar mass of N2 so that we can get that value. That becomes 28.02 grams of N2. And that gets us 14.9 grams of nitrogen gas that's produced. And then we got to do the same thing, right? That's our first reactant. We got to do it with the second reactant. So the 90.4 grams of CuO. For the sake of time, let me go ahead and just throw in what it would look like. All right, so throw that on there, and again, going from grams of copper oxide, applying the molar mass, the mole ratio, the molar mass of nitrogen, then gives me 10.6 grams of nitrogen, could be produced for both of these, right? So these are, again, hypothetical amounts. If I react each of the reactants, how much of that same product will be produced? Because this one produces less, our limiting reagent ends up being 90.4 grams of CuO. The follow-up question, right? How many grams of N2 can be isolated, right? Basically, how many grams of N2 is made. That's then going to be answered right here, right? This is going to take care of it. So that's the second answer. Kind of missed the box there. But that's the second part of the question. Just 10.6 grams of N2, instead of being could be produced, is now just produced. And that's how much is supposed to be made. And to finish it off, right? This problem, if a sample, same problem from the previous slide. Same problem here. 18.2 grams of ammonium reacted with 90.4 grams of copper oxide. How much excess reagent remains in the reaction mixture? So we make them happen. We recognize, remember, this is going to be our limiting reagent. And this is going to be an excess. So let's go ahead and do a little bit of work where I go from my limiting reagent to my other reactant. So it's going to look like this, 90.4 grams of CuO. Speeding things up a little bit. Okay, so again, using the information from the previous slide, 90.4 grams, 79.55, 2 to 3, 17.03, right? Molar mass, mole ratio, molar mass. To go from CuO, one of the reactants, my limiting reagent, to the other reactant, this one in excess. So that ends up being 12.9 grams of NH3 that is used up with the 90.4 grams of CuO. Then, to finish it off, do a little bit of math. I'm provided 18.1 grams of ammonia. And then I'm going to subtract the 12.9 grams that is used, and that's going to result in 5.2 grams of NH3 remaining. That says remaining, which is your final answer. Alrighty, that'll do it.